All right, welcome back everyone for another deep dive. You ready to get into some really cool stuff today?
Absolutely. Always ready to dive in.
Awesome. So today we're going to tackle something that's, well, it can be kind of brain-melting quantum measurement,
Yeah, it's one of those topics that can make your head spin.
for sure. But we've got a really interesting source this time. It's this article summarizes a lecture by Harvard physicist Jacob Barandes. And let me tell you, he offers like a whole new way to understand this quantum weirdness, and it really blew my mind.
Yeah, his approach is really refreshing, I gotta say. He gets away from a lot of the jargon and tries to make it more intuitive, which I appreciate.
Right. That's what I loved about it. So, like, he starts with this idea of indivisible stochastic processes.
Right, those are key.
And I got to be honest, the first time I saw that phrase, I was like, whoa, hold on. What? But once you kind of unpack it, it starts to make sense.
Yeah.
So, stochastic, that just means random.
Yeah, exactly. Random or probabilistic.
Okay, cool, cool.
Uh,
But then what's the deal with indivisible?
well, think of it this way. Imagine flipping a coin. You can't really have half a coin flip, right? It's like one complete action, one indivisible process.
Right. You flip it, it lands heads or tails, boom, done.
Exactly. And that's what Barandis means by indivisible. These processes, they're kind of like the fundamental building blocks of reality at the quantum level. You can't break them down any further. And the outcome, just like with the coin toss, is probabilistic. It's not predetermined.
Oh, okay. So you're saying that reality is built on these tiny, like, coin flips that are constantly happening.
In a sense, yeah. It's a really wild idea, but it helps us understand how quantum measurement works in a much clearer way.
Okay, I'm starting to see where this is going. But how does this whole indivisible stochastic process thing actually change the way we think about measurement?
Okay, so the traditional view of quantum measurement, the one they teach in most textbooks, is that when you measure a quantum system, its wave function collapses.
Right. The wave function collapse. That's the classic explanation.
Exactly. But that always kind of felt like a cop-out to me, to be honest. Like, what does collapse even mean?
I know, right? It's like they're just saying, poof, magic happens. And we're supposed to be satisfied. Never really sat well with me.
Exactly. And I think Barandis feels the same way. He offers a much more, I guess you could say, satisfying explanation. He says that measurement is really just a special kind interaction, like between a particle and the device that's measuring it. But here's the key. This interaction, like everything else at the quantum level, is governed by these same indivisible probabilistic processes.
Okay, I think I'm following. So instead of this mysterious collapse, it's more like a cosmic coin flip that decides what we observe.
Yeah, that's a great way to think about it. The measurement itself becomes part of this, this probabilistic dance. And here's where it gets even cooler. The environment plays a huge role here, too. It's not just some passive bystander.
Oh, interesting. The environment. You mean like the air around the particle?
Yeah.
Or even like the measuring device itself?
Exactly. Both of those things, and even more. Barandis's approach, it really emphasizes the importance of decoherence. You familiar with that term?
Vaguely. Remind me.
Sure. So decoherence is this idea that as quantum systems interact with their environment, they kind of lose their quantumness, their ability to be in multiple states at once. They become more, well, classical.
Okay, I'm with you. So decoherence is like the environment is kind of nudging these systems during those cosmic coin flips, influencing the outcome of the measurement.
Yes, that's a fantastic way to put it. And these nudges, Barandis, he calls them division events. Imagine like a leaf falling from a tree. A gust of wind can push it this way or that way. That's kind of like a division event. And all these little nudges shaped by the environment, they add up. They guide the system towards a specific outcome.
Whoa. Okay, so let me see if I've got this straight. Brandis is basically saying that we should think of measurement as a natural consequence of all these probabilistic interactions with the environment, not as some weird magical collapse.
Exactly. And that has some pretty wild implications. Like, he even suggests that things we normally think of as totally classical, like a table or a chair, could actually exhibit quantum behavior under the right conditions.
Wait, what? Seriously? A table could be in multiple states at once. How is that even possible?
Well, that's where things get really mind-bending. We tend to think of the quantum world and the classical world as totally separate, but Barandis is suggesting that the line between the two might be much blurrier than we think. Maybe quantum mechanics is more fundamental to reality than we previously thought.
Man, that's heavy stuff.
Yeah.
So much for those neat little categories, man.
Right. This whole approach, it really challenges our assumptions about how the universe works.
It really does. You know, what really gets me thinking is this. If everything boils down to these probabilistic events, these coin flips, does that mean the universe is essentially random? I mean, how can there be order and structure if it's all just chance?
It's a profound question, and it's one that physicists and philosophers have been grappling with for a long time. If even classical systems can exhibit quantum behavior, what does that really mean for our understanding of reality? What does it say about the nature of cause and effect? Free will. It's a lot to wrap your head around.
It really is. And I think that's a perfect place to leave it for today.
Okay.
A big thanks to everyone for joining us for this deep dive into the wild world of quantum measurement. It's definitely given us a lot to think about.
It always does. And who knows, maybe we'll find some answers, or even more questions, in our next deep dive.
Until then.
See you next time.